Hello everybody. Today in this video we will be discussing about the complex plane. Now if you've been in high school, then you probably know what the Cartesian plane is, which is simply the XY axis. And now let's introduce the complex plane, which is similar to the Cartesian plane, but the only difference is that the two axes represent the real axis and the imaginary. This concept can be used in practical uses such as capacitors and inductors, and these subject will be discussed in the next video. So back to the complex plane. How do we compute numbers when it is in the imaginary axis with the real axis? Here are a list of equations that showcases all the different complex identities. So the real values would represent an ordinary number like 2, and the imaginary would represent a number with a coefficient j beside it, so 2j. Now we got our real values and our imaginary values. Now let's discover the complex identities. When you have two imaginaries multiplied together, such as in this place, j squared, what you will get is -1. So if two imaginary numbers multiplied to each other, they will equal to that negative of whatever the magnitude of those two terms are. Next is having the imaginary number below a fraction, such as in the denominator. If you have this case, in this scenario, what you will get is -j. Now let's go into other identities. If you add up two imaginary numbers together, you would have in this case 3j. So the j stays the same compared to having two imaginary numbers multiplied by each other. Same thing goes with subtraction. When you subtract two imaginary numbers, it will still remain as an imaginary number. So here we have j minus 2j, and what we get is -j. And then getting back to the concept of real values, if you calculate two real values together, you will get a real value in the end. So we have 2 times 2, and that equals to 4. And this, as we can see, is the polar opposite of having two imaginary numbers multiplied to each other, where you will actually get a real value. Next is having a real value multiplied by an imaginary number. And so forth, what we get is an imaginary number. And in this case, we have 2 times 2, and what we get is 4. And we have this j here, so what we get is 4j. Now, I've already did this answer, but if we have an imaginary number in the numerator and then we have a real number, it's really simple. You just have that imaginary number along in the answer. So now that we've finished covering some of the basic concepts of complex identities, let's look at some sample questions. So what we have here is the numerator, which is 3 plus 2j, divided by the denominator, which is j. Utilizing our knowledge about having the imaginary number in the denominator, this will determine what our answer will be. So what we have is, when we split these two terms up, we have 3 over j plus 2j over j. Now, For the first term, we have the imaginary number in the denominator. So what we get is 3 minus j. For the second term, we have the imaginary number in the denominator also, but we also have it on the numerator. So what happens is that we cross those two terms out, and what we get left is positive 2. And our final answer will be 2 minus 3j. Our second question here, we have two terms, and we have to multiply them. So what we get is, by using our method of expansion, we have 4 multiplied by 4, and then we have 4 multiplied by negative 2j, and then we have positive 2j multiplied by 4 again, and then we have positive 2j multiplied by negative 2j. Now let's get our answer for each single term. So what we get is 4 times 4, which is 16. 4 multiplied by negative 2j, we get negative 8j. Positive 2j multiplied by 4, we get positive 8j. And positive 2j multiplied by negative 2j, what we get is negative 4j squared. Now, deducing these four terms up into the simplest form as possible, that is the objective of any mathematical question, we get is we cancel these two terms out, negative 8j plus 8j, and for here, utilizing our knowledge about having two imaginary numbers multiplied by each other, what we get is negative 4 and then a negative 1 here. Because of the fact of this term, we get this answer. And then we're going to be left with 16. And now what we have is 16, negative 4 multiplied by negative 1, that is plus 4. And then we finally get 20 as our final answer. Now that we are able to compute numerical questions when it comes to the complex theory, we have to analyze the complex theory in a graphical sense. So now, to explain it in graphical sense, we're going to have to learn about the rectangular form and the polar form. So on and so forth, all our ideas are translated in rectangular form. And rectangular form is basically the form of x plus yj, with x being the real value and y being the imaginary value. And in this plane, to illustrate that in the complex theory, we have x value here and then yj value up here. And whatever values our x and y is, so for example, let's have x as 3 and then y as 4. To illustrate that in the graph, it's easy. So we have 3, so we can mark this, draw it right here. And then for the value of 4, that will be slightly greater than this value here because x is smaller than y. So we can draw that line here. Now this is the rectangular form explained in a separate division. So we have a real value and an imaginary value. But what if we want to combine them together? If we combine them together, we be given an angle and its magnitude. And that's where the polar form comes in when we are trying to illustrate that in a polar form, vice versa. So the polar form would essentially be this value with an angle on it. And this value of the magnitude can be deduced by the Pythagorean theorem. So this magnitude, we can call it z. Z is simply equal to the square root of x squared plus y squared. This is the Pythagorean theorem. And the angle, using trigonometric knowledge, this angle is equal to the inverse tangent of y over x. So that is how we could deduce the complex plane into a graphical sense, and that is split into the rectangular form, x plus yj, and the polar form, I forgot to write that is z, and this angle right here, theta. So that is it for this introduction in the complex plane theory. I hope you enjoyed this video, and I will see you next time.